Hi, in this section we'll talk about how to use the derivative to find maxima and minima. If you draw a function and you know that at either a maximum or a minimum point, for example, you can see that the slope of tangent line may be 0, which is actually the derivative, if you recall, f prime of x, or it could be vertical, which is undefined, like at this sharp or cusp point. So if we keep that in mind, and then we use this definition for critical numbers, or we'll actually use the critical points in a little bit, is x such that f prime of x is 0 or undefined, but f of x, the original function, is defined. So for example, asymptotes do not count as critical points. Basically, critical numbers or points are candidates for maxima or minima. We don't know what they are exactly, so we will have a chance to test them in a little bit. So let's first define relative extrema, or maximum or minimum. So f of x has a relative maximum at x, let's say, equals r, if f of r, the y at that point, is greater than or equal to f of x for all the nearby points. So let's say it's some interval. And that should make sense if you have a relative maximum, for example. It would look like this, if I can draw it. So right about here, notice how at this point all the nearby points are smaller. It may not be the highest point of the function. For example, the function may keep on going, but relatively speaking, it is the highest. And very similarly for the lowest, relative minimum at x equals r if the y at that point is less than or equal to the nearby points, again on some interval. And of course, we might also have an absolute maximum or minimum at a point. Let's say we have absolute maximum at x equals r if f of x is greater than or equal to, now actually this should be f of r, there's a little typo. F of r is greater than f of x, and all the domain or the specified interval, which in a lot of problems will just focus on the specific interval, not maybe the overall domain. And same thing, absolute minimum, again, if f of r at that point is less than or equal to, again, the lowest point. So we're talking about, we will take endpoints as also possible maximum or minimum. Now, something to keep in mind that you may have more than one absolute maximum if you have a point, let's say, that is the same y. Let's say you have these two maximum points and they have the same y, whatever it happens to be, and that means you have, it's really the same absolute maximum, but it may occur more than once, maybe at a more specific point. So you may have it, for example, y equals 100 at x equals 2 and x equals 5. So you may have two distinct points, 2, 100 and 5, 100. They're both absolute maximum because they're the highest. And this one does not have absolute minimum if we draw it. Let me get back into drawing. Yeah, if the function keeps on going down here, then it may not have an absolute minimum. So if a function goes to infinity or negative infinity, it does not have to have an absolute max or min by any means. So critical points, the way we defined them from before, what if we define them in three different ways for us? For example, stationary is x such that the derivative at those points is 0, versus singular x such that f prime of x is not defined, but f of x, the original function, is defined. Again, it's usually when it's a sharp or cusp point, for example, and endpoints of a closed interval, for example, a comma b, if they're included. Critical points, including endpoints of the interval, are candidates for maximum or minimum. And it does not necessarily mean if so let's say slope of tangent line is 0 at a particular point, does not necessarily mean we have a maximum or a minimum. We could have an inflection point, and how do we tell? We can tell by the sign of the slope of the tangent line. For example, the function's increasing, may slow down a little bit and continue increasing. So we may have an inflection point there and not maximum or a minimum. Now let's put our knowledge so far to use. Can we classify, find all relative and absolute extrema of the function? We don't know enough yet to do it, but maybe if we know enough about graphing, let's see how it works if we just find critical points and then go from there. So let's say we have function x squared minus 2x, and we have an interval from 0 to 4. Then we can find critical points. Again, we find the derivative first, which is 2x minus 2. For stationary, we set it equal to 0. We solve for x. We get x equals 1. For singular, we do not have any. Typically, we do not have any for many of the polynomial ones. Let's say 2x equals 2. Usually this kind of the polynomial derivative is always defined. So by defined, we mean if any x that we plug in into the function, do we get an actual y value or the actual answer. So for example, if you have a denominator and you're dividing by x, if the function is not defined at a certain point, then that could be a candidate for a singular point. But it's usually not an issue for polynomials. And we do have a couple of endpoints, 0 and 4. So in this problem, how do we classify if they're maximum or minimum? Well, we can find the y values if we plot them in the table like this. So 0, 1, and 4. If we plug them back into the original function, x squared minus 2x, we get 0 for 0, negative 1 for 1, and 8 for 4. And if we quickly graph it, it's a parabola. It looks like this. It's easy to see that 0, 0, the origin, is actually relative maximum. Why is it's a maximum? Because all the nearby points are slightly lower. It starts decreasing from that point, which is why it's a maximum. Then it's relative because it's not the highest. And then looks like negative 1, 1, negative 1 is a relative minimum. And 4, 8 is actually an absolute maximum because it's the highest. So we can essentially classify points if we know how to graph it or look at graphing calculator. But there is another method that we can not necessarily rely on graphing, and that's first derivative test, and that's what we're going to use. So to find max and min on a closed interval, we can use the following method. This helps for absolute max or min. If we have a closed interval and the function is continuous, then the highest y value is absolute max and the lowest y value is absolute min, which is kind of nice to know. But it has to be continuous, so no asymptotes within that interval, so that way it doesn't go to infinity or negative infinity. And it has to be a closed interval, so it only works sometimes. Now let's talk about first derivative test. To find max or min, we can perform first derivative test. How do we do that? First, find critical points as outlined above. Then create a number line plotting critical points in order from least to greatest, preserving the order of the number line to see where f prime of x is positive or negative, because we can tell whether the function's increasing or decreasing. For example, if you notice that the derivative, so we're plotting points into the first derivative, f prime of x. If the sign changes from positive to negative, so the function's increasing, slope is positive, reaches a maximum and starts decreasing, so slope becomes negative, then we have a relative max. So this test essentially tells us about relative max or min. To find the absolute max or min, we need the actual y values. Similarly, if you notice, we have a relative min. If the function is decreasing, it switches from negative to positive. So it's decreasing, reaches a minimum, starts increasing. So it has to switch sign in a particular order. And we may have no relative extrema. Maybe it's a possible inflection point, although more information is needed, but the sign does not change. So it's either decreasing, may slow down, or speed up, depending on if the sign is undefined or 0, and continue, let's say, slowing up, decreasing, or vice versa. So if there's no change in sign, we do not have an extrema at that point. Endpoints are a little bit trickier. I usually visualize it when I do the first derivative test, but notice for the left endpoint, we may have a maximum. Again, I do not memorize it, but the slope typically would be negative if you notice the function's decreasing from that point. And vice versa, the right point, endpoint, the function's coming up to it. So the slope is positive, but the function's coming up. Again, all the nearby points are a little bit smaller than the endpoint. That way you have a maximum. Minimum, on the other hand, we have a minimum if the function's increasing from that point on the left endpoint, and So we have slope is positive, and vice versa on the right. If the function's coming down to it, so the slope is negative, then we may have a minimum. Now let's put our knowledge on to use on some examples. Find the exact location of all relative and absolute extrema for each function. So let's say we have x squared minus 4x plus 1 on 0 to 3. Again, we can find critical points, find the derivative first, which is 2x minus 4. Then for stationary points, we set it equal to 0, x is 2. For singular, again, there is none because the derivative 2x minus 4 is always defined. There are no issues. You can plug in any x. There are no problems. Endpoints are 0 and 3. It's as given above. So we have 3 critical points, 0, 2, 3. So we can plot them on the number line. This is how I typically do the first derivative test. I indicate the endpoints with a bracket so it's clear that these are endpoints. Then I plotted the 2. The endpoints are kind of the free points because you can plug them into the derivative and look at the sign because you will get a certain sign. So whenever you have endpoints, try plugging them into the derivative. So let's say 0, if you plug it into, if you recall, f prime of x, I believe, was 2x minus 4. I think that's what it was. Now let's double check on that. Yep, 2x minus 4. So let's go back. So if we plug in 0 into 2x minus 4, the sign of the first derivative is negative. It's negative 4, so the original function's decreasing or going down. So we know that. At 2 it was 0, so the function is, because it was a stationary point, the derivative is flat, or 0. And then at 3, if we plug in 3 into 2x minus 4, 6 minus 4 is positive 2, so we get positive, so the function is increasing. So if you note, at the endpoints, at 0, we have a relative maximum because notice how the function is going down from there. So all the nearby points would be lower than that point. At 0, notice how we switch from decreasing to increasing. That's why I drew the arrows in this way. It's actually easy to visualize that you have a minimum right at that point. And at 3, once again, we have a maximum. Why it's a maximum? Because we're coming up to that point. So it may look something like this. And right at that point, all the nearby points are smaller than that point. So we have a relative max. How do we know if they're absolute? Well, we find all the y values by plugging them back into the original f of x. So that's what we get. If we have 2 maximum points, and notice how the highest one, because we have a continuous function, a polynomial within a closed interval, so the highest y value is absolute max. The lowest y value for the minimum, since we only have one minimum, it becomes absolute because it's only one minimum, so it's the lowest. And then 3 was another maximum, but the y value was smaller than 0, so it stays relative maximum. And that's typically the idea how you can do it for a lot of the problems the same way. Let's take a quick look for higher degree. Let's say x cubed minus 12x. If you have a higher degree like that, it's helpful to factor. I'll show you why, because the signs are much easier to tell if you factor a function. And so once again, we find derivative. For polynomials, it's generally very easy. 3x squared minus 12, set it equal to 0. Notice how we can pull out 3. And then further, we can factor it as, let's say, x minus 2 and x plus 2, the difference of squares. It's good to refresh factoring here. So we have two points here, 2 and negative 2. Once again, we have no singular points, and we do have a couple of endpoints. So we actually have 4 points here. So let's take a look. I plotted them all on the number line again, indicating the endpoints with brackets, so it's easy to see. So again, the endpoints, we can just plug them into the derivative. Let me write it somewhere nearby so we can see where it was. I believe g prime of x was positive 3 times x minus 2 times x plus 2. And again, the reason why we keep positive 3 is to check the signs. So we can plug in negative 4. For example, it's very easy to check. 3 is positive, so I keep the positive on outside of parentheses. Then I'm plugging it into each parentheses. Negative 4 minus 2 is negative. So that's the first parentheses. Then negative 4 plus 2 is still negative. And this is all a product. Positive times negative times negative. The end result is positive, which is, you notice, the same thing right here. So the function's coming up from there. This time we have a relative min because function's increasing from that point. Between negative 2 and 2, the two stationary points, we actually, to check the sign, we need to pick a point to check the sign of the derivative. So we pick the easy one, let's say 0. You can plug in x equals 0 into the derivative. And you can do the same thing. Quickly note the signs. Looks like 3 is always positive. Inside first parentheses, it's negative 2, so it's negative. Second parentheses, it's positive 2, so it's positive. So the end result is negative, which we note right here, so function's decreasing. So at negative 2, we actually have relative max. And at positive 2, to the right of 2, we have another endpoint, which we can plug in. So that's the last one we plug in, x equals 4. And same thing, we check the sign. This time, all 3 of them are positive, so the result is positive as well. And so that's what we have. Again, looks like 2 is a relative min. But at 4, since the function's coming up to that point, we have a relative max. And then I just basically plug all 4 of them into the original function, f of x. And notice how I get negative 16, 16, negative 16, and 16. Since they're all the same y value, well, negative 16 and negative 16, they're both minimum. So they qualify for absolute because they're the same y value. If you remember, if it's the same one, then they could both be absolute. Same thing for the maximum. They're both absolute maximum. And that's it. Now, let's do one more example. And maybe we'll do more advanced examples in another video. But just to wrap it up, let's do one more, a quick one. Let's say if we have t cubed plus t from negative 2 to 2, we have critical points. Once again, we try to find stationary points. But if you notice the derivative, 3t squared plus 1, it's actually never 0. I mean, you can move the 1 to the other side, and it's not possible to have a positive squared equal to negative 1, not with real numbers. So we may not have any stationary points. We also do not have any singular points because derivative is always defined, but we do have 2 endpoints. So sometimes you may only have endpoints. So you can still test them, and it looks like this, negative 2, 2. You can plug them both into the derivative, which was 3t squared plus 1. Both negative and 2 would give it a positive value. That's why they're both plus. So the sign never changes. But nevertheless, you can still tell it's positive, so the function's coming up. So you actually have a minimum at that point. And it's also positive at positive 2, but this time it's the other way around. The function's coming up, so you have a maximum at that point. And then you can find the y values. And again, because it's only a single minimum, and it's a continuous function on a closed interval, we have absolute min at that point. And we have absolute max and the other endpoint. And that's it for this video.